Okay, so I hope everybody can hear and see me, and I will be recording these lectures and putting them on YouTube and share the links to you on AutoClass. If you have questions, feel free to write in the chat box or unmute yourself to limit background noise. Please mute yourself if you're not going to ask a question or not speaking. But I mean, feel free to unmute yourself at any time. You can interrupt me anytime during class if you want to add something, ask a question, make a comment. Okay, just I want this class to be as interactive as possible, even though we are not face to face. Still, I think even the synchronous lectures give some kind of a face-to-face feeling. Last year, this format, it was really interactive. Students were asking questions in class. I had fun teaching this class last year. I hope it will be similar this semester as well. So, yeah, if you have any questions, feel free to use the chat box. Sometimes you cannot send a message to everyone. I mean, we had some problems before in WebEx, but maybe they may have updated it. They may have solved this problem. At least 3 of you were able to send messages to everyone. But if the message only comes to me, I'm going to repeat it for everyone. If you have questions, comments, use the chat box, or as I said, unmute yourself and speak up. That's also fine. So today the plan is we are going to have 2 hours today. We are going to start right away, although this is the first meeting. I will give an introduction to what computer graphics is. I will talk about the main focus points that we are going to cover this semester. We cannot cover the entire area of computer graphics. It's a huge research area with constant developments every year. It has applications in game industry, movie industry, some scientific visualization. We are going to talk about these today. But in general, we are going to talk about three-dimensional graphics. So it's although I'm not my main research area is not computer graphics, but I like teaching this course a lot because it's this course, the whole semester tackles a very well-defined problem. And the methods that we're going to see are very well established. And it's something that when the code you write with the mathematics, with simple physical modeling, very simple physical modeling we will be using, you're going to see that we'll be able to generate our C code, or C++ codes will be able to generate images that look really nice. It's really rewarding getting that experience. Maybe this will be the course to show your parents what you can do with programming. Previously, maybe you may have shown them, oh, this is what I do. I code like this, and you may have shown them some textual output which doesn't make sense to them. This is the course where you can say, I wrote this program that generated this image. So this is therefore the output is visual, and it's really a rewarding experience. Your bugs, I mean, sometimes students are, especially in homework assignments, sometimes you get lost in details. Sometimes when you compare two images, even single pixels, you don't want to lose points from those single pixels. But overall, I mean, your bugs are also going to be also present themselves as simple differences in the generated images. Sometimes they will be acceptable, but usually when we are grading the homeworks, we are not doing a black box testing. We are not going to compare images between the solution and your images by using a program. You will do it manually by just looking at those images. And if there are no perceptible differences between them, you will get a good grade. But sometimes students, they grade themselves harsher than us, so they try to tackle on very simple small problems, but that's good. Sometimes we find students find bugs in our solutions. Sometimes we may have bugs too, but this is what we will be doing. We will be generating images by writing programs. So when we talk about images, is this an image processing course or a computer vision course? No. What is the difference between computer graphics and computer vision and image processing? All these things. I'm going to talk about them, these differences today. So it will be a short introduction, and it's also graphics, although the acronym that you use between your friends is always graph course. Okay, so this is graph. This is not related to graph theory either. So you're not going to be seeing graph theory algorithms. Computer graphics is the problem of generating images of virtual three-dimensional worlds. This three-dimensional may change in different definitions. In this course, we will be focusing on this definition. We will have a three-dimensional virtual world defined somehow, modeled and given to us as input. And with certain parameters like the camera location, camera orientation, the light in the scene. If there is no light in the scene, we will be just generating black images. So the light position, the light type in the scene, there should be a light source, there should be a camera. So just think about how we see our world around us. So it's a good, this course is also a good way to have an understanding between real life, and how we can model things in real life by making certain assumptions, abstractions, model them on computers. So it will be a good mapping between real life phenomena like seeing our world and how we can model this on computers. So it's also well, these are the aspects that I like this teaching this course. Okay, so I'm going to give all those, I'm going to show you examples. So today is going to be really fun. Lots of images, videos. We are going to see how computer graphics is very well established. I mean it's a field that I think one of the fields that has reached its ultimate goal. We can now generate real-time images, in, for example, 50 images per second speed. When I say real-time images, with dynamicity in the scene, things changing, moving, and the generated images cannot be distinguished from real-life photography. So that was one of the ultimate goals of computer graphics. Can you generate images with so much detail, with modeling the real life in so much accuracy that the generated image looks just like the real photograph? That's one of the goals. But and we can do that these days. So what does that mean that all the problems in computer graphics are solved? No. Just take a look at the proceedings of the ACM SIGGRAPH. There is the flagship conference for computer graphics is the SIGGRAPH conference, Special Interest Group in Graphics by ACM. Every year there are lots of papers published there, and people are still doing research in this area. And in our department, the two faculty members who do research in this area are Oğuz Hoca, Ahmet Oğuz Akyüz, who will be teaching section 1, and Yusuf Sahillioğlu Hoca. Yusuf Sahillioğlu Hoca does some digital geometry processing, but he's also, the research he's doing is related to computer graphics. Okay, so if you're interested in computer graphics and want to do graduate studies, you may contact them and see what they're doing these days. Okay, so I will be teaching with Oğuz Hoca. It will be 2 sections, and officially you may be in either of these sections and you may attend any of these sections. It doesn't matter. Your official section does not matter. You're not going to take attendance. We are not going to have synchronous quizzes or anything. So you may be in section 1 and you can attend section 2 or vice versa. That's perfectly fine. Everything will be synchronous between synchronized between these 2 sections. Midterms, final exams, 1 midterm, 1 final exam. They will be jointly conducted together. There will be 3 assignments, 3 programming assignments. and you will be able to do them in pairs. If you want, you can do it individually, but you may pair up with your friend and submit a group project, group assignment solution. There will be 3 programming assignments throughout the course. I mean, this course, let me give you some feedback from previous year's students. You probably know these feedbacks better than I, because you have some. I mean, you have a network within yourself. So, but usually this course, people may say it's a difficult course because the programming assignments are very difficult. But if you follow the lectures weekly, and if you start the assignment as early as possible, they're not very difficult assignments. I also did code some of them myself. I do it in parallel with you, the new assignments, and they're not that really difficult. The only difficulty is that there will be certain things that you're going to be facing the first time, like the OpenGL library in the second or third assignment. In the third assignment, we will be talking about OpenGL. Setting up an OpenGL development environment may be tricky at first, but if you do it as early as possible, even before we post the assignment, you'll be and play with some sample programs, example programs that we will provide. You will get used to it as quickly as possible. I mean, if you just start the assignment in the last 5 days and set up your OpenGL environment in the last 5 days, it will be really difficult to finish the assignment. So get acquainted yourself with these libraries. And I mean, we're not going to talk about OpenGL starting in the first week. We'll actually, it's in the second half of the course. We will first start with ray tracing algorithm. That will be the first algorithm to solve the same problem. So it's interesting that we will be solving the same problem by using 3 different methodologies. The second and third methodologies are basically they're the same algorithm. One of them is an already ready implementation of what is called the forward rendering solution. OpenGL implements that, and we will also do it manually ourselves in the second assignment. In the first part, we'll talk about ray tracing, which is a different method to solve the same problem. It's called backward rendering. So backward and forward rendering. What are these things? So backward is like, we're basically, these algorithms are named based on how we trace light rays. So yeah, let's think about that. Talk about this actually. What we are going to do in this course is going to be simulate how we see our real world around us. So how do we see? We have 2 cameras, our eyes. So our eyes are 2 cameras, so we have stereo vision. But even if you close one eye, you can still see the world around. And maybe you don't remember depth at first. So there's a lot of things going on in the brain. So there's a lot of cognitive aspects of what we see. But in this course, just focus on the image. Just look at some place, stay still. You're basically taking a photograph of the real world. What are the factors that, I mean, how can you see the real world? Obviously, light rays are coming to your retina, hit certain cells in your retina, they excite them, they're photosensitive cells in your retina that are excited by these. The different wavelength of the photons gives us color vision. But for example, how do we see perspective vision? Or so one of the factors is light. There has to be light. Without light, we don't see anything. So photons are the main actors that help us see. What are the other things? So we have to have a camera. The camera, our retina, that the photons hit. So let me use I'm going to be using this as my blackboard. This one. So light rays are coming. Okay, to our retina. If this is our retina and there are some photosensitive cells, they are passing the our lens. I don't know the biology of the vision that well actually. So some of the things I may say here may be incorrect, but the basic things are what happens is that light rays pass through our pupils and they hit certain photosensitive cells in the retina. So, but what are these light rays, for example? What is the color of this light ray? There are different colors. For example, what determines this color of the light ray that comes to our eye? It's probably this light ray is some ray bouncing off some object, right? There may be some blue ball. Let's have some blue color here. There may be a blue ball that is here, and this light ray actually be of color blue that is coming to our retina. So why is this blue and why is it bouncing off this? So there may be some light source, and in our world, for example, the fluorescent lights in my office are such light sources. The sun is the if during daytime you have sun as the light source. At night we have the moon, but we have light sources all around us. So there are certain things as light sources. In this course, we will be focusing on a very simple model of a light source. A point light source, actually we will maybe talk about directional light sources as well, but a simplest light source that you can model in such a graphical virtual scene is a point light source, which have a location and which emits light in all the directions. So this light source, there are light rays coming off of it, and some of them are bouncing off the surface of this ball and hitting our eye. So we just started modeling, doing certain modeling, for example. And as you can see, there will be lots of simple mathematics, some linear algebra, some simple geometric operations, some vector algebra, like for example, how do you know if this light ray coming off the surface of this ball, where is it going to bounce to? Or which of these rays are coming from which part? So what is it? All these angles, there will be angles that this light ray is hitting the surface. Based on the surface orientation, that light ray is going to be but these light rays that are bouncing off in different directions, they're not reaching the retina. So they're not going to be the ones to generate the image in our retina. So our goal in this course will be to solve this problem. We will be given a virtual world definition. We will be saying that, for example, there is a blue ball at this coordinate with this size, with this color. There is a light source at this position with this color, with this intensity. This is a light source. There's a camera at this location looking at this way. Okay, so we will be, our world is going to be maybe composed of very complicated objects. There may be a tree here, okay, a pine tree, or there may be a house, okay, or mountains. So you may have this virtual world defined in, we are going to see how we model these virtual worlds. But they will basically be sometimes polygonal objects, sometimes mathematical definitions of geometries, like this ball. If it's a sphere, all you need to do is indicate where the center is and its radius is. Okay, that will be the geometry for that ball. If it's a perfect sphere, you may just need these numbers. That's center location, its radius, and also if you need the color, you may need the color information as well. But we will be modeling a virtual world like this, and we will indicate the additional parameters, how many light sources are there, where are they, what are their intensities, and we will say, I have a camera here looking at this from this direction to this virtual world. What does this camera see? Paint me that picture. And we will be doing that by writing code, okay? And we will teach you the algorithms. The first algorithm that we will have, the backwards rendering algorithm, it will trace the light rays back from the image towards the scene. So it will, the ray tracing traces the light rays backwards. For example, this, because since we don't know the color of this yet, we will start tracing this back, and we will see that, oh, it hits this blue ball first. Okay, then what is the color of this blue ball, and where is the light source? How much of the, what is the intensity of the light ray that is coming here, depending on where the light source is. For example, if the light source is behind the ball, maybe we will not be able to get a bright color, or if depending on its orientation, we may get different intensity light rays. But we will be tracing this rays backwards towards the scene, and we will follow them in the ray tracing algorithm. That's the first algorithm that we will see. And then we are going to, in the forward rendering algorithm, we will do something different. We will just say this vertex of this object, which pixel does it contribute, which pixel does it project on? We will, this will be called the forward rendering algorithm. So it will be like a point of view of the objects in the scenes. It's a much more efficient algorithm because it's at the vertex level. We will be doing these questions: where does this vertex, this point of this tree, falls on my image, which pixel? So, and this, the algorithm that we will see is basically just simple mathematics. You'll see it will be a bunch of matrix multiplications, but incredibly, this is what we will have. If you have the XYZ coordinate of a point in the 3D world, by multiplying this 3D world with a matrix, it will immediately give you what the pixel coordinates of this pixel of this three-dimensional point should be. Which pixel, if it was if there was a ray coming off this, which pixel it would contribute to. Okay, so we will see these algorithms. So this is just a very crude overview of what we will be seeing throughout the semester. So we will talk about, for example, things like how instead of having a single color blue ball, can we have textures on them? So texture is a new term that you may have heard, but it's basically saying the ball has different colors and different places on its surface. So how do we map such a texture onto this ball? How do we have, for example, perspective vision, or in which faraway objects are going to appear smaller? Things like that. We are going to see all these mathematics, and the math that we are going to see, it's not actually there are different models of computer graphics which use integrals and calculus and very heavy math. In this course, we are not going to be using any of these heavy math. It will be pretty simple, just multiplication of vectors, dot product. We will be using cross product a lot. So just some vector algebra, some matrix multiplication, and very simple mathematics. Okay, so the math in this course is not very elaborate, but we will be doing some vector algebra. And okay, so that's what we will be doing. So that was a general overview of the course, and I will show you some example images before we go on. For example, this was the first time we gave ray tracing in this course. We needed some sample virtual scenes, and this is a scene that I designed, and this is an output of, I mean, I say I designed. What I did was I just put these different objects onto a table in different places. Okay, so this mug that you see here on the right hand side, it's downloaded from turbosquid.com, I think. So let's go. Let me show you those websites. Turbosquid. So 3D models for professionals. I'm not a professional, but there are also 3D models for not only professionals. You can have free models. For example, let's find a different mug. Coffee mug. Yeah, I think this was the mug that I use. Coffee mug. So this is basically an online store for your virtual objects. So what does it mean to be a virtual object? So when you go into this store, it looks really like Amazon or any online store, right? Oh, there are couches. Oh, you can get lots of things for home decoration. Oh, if you need certain things for your kitchen, here are those kitchen objects. And these objects are, so what does it mean for them to be virtual? It means they don't exist in real life. So what are they then? They are basically geometry. So I think this is the coffee mug that, but this one is $39. So they also come with the price. So how come if it's not real, I pay $39 for this coffee mug? Because there are modelers who work on their computers and spend hours and hours to make these virtual objects. Just like, so when I'm doing some painting on this GIMP, what am I doing? I'm generating certain virtual things, a virtual tree. So would you pay $39 for this tree? No. I mean, it's just a two-dimensional sketch of a tree. So these modelers are three-dimensional sketchers, actually. They sketch, just like sculptors, but like virtual sculptors, they sculpt this virtual mug by using programs like Maya, Blender. There's one free program for you to use, which is called Blender. You may go ahead and give it a try. These tools are really complex. It takes time to get used to these tools. They have very complex interfaces because basically what you're trying to do is you're trying to do some sculpting a three-dimensional model by just using your mouse and keyboard and a two-dimensional screen. And the two-dimensional screen is your window to the 3D world. So usually when modelers see the same scene from different perspectives at the same time, and they can add new objects. For example, adding these objects are very simple objects. If you look at, let's go ahead and take a look at this scene again. Look at this cube. Would you pay $39 for this cube? No, because it's a really simple object. How can you define a cube in 3D? All you need to do is define these four vertices, and you can have, if you need to have a coordinate system. And generating a cube is not very difficult. If you know, for example, this corner, and if you know the size of the cube that you want to generate, you can generate the other corners automatically. Finding a mathematical rule for that is very simple. So basically this cube can be composed of 6 squares put together in a certain way. And these two spheres are very simple to model, perfect spheres. All we need to do is, as I said, specify its center and a radius, and then give it a color. Here, these two balls, they have different colors. They also have different, there's another difference between them. Can anybody tell? For example, this is a green ball, this is a red ball, but is it just the color that is different between them?
No, one of them is shiny and
Exactly.
reflecting, and
Ex
the other one is
yeah, so some material
white.
properties, very good. So you can also see the material properties are different. So this is really reflective, and we can actually see the horse. This is like a mirror. We can see the horse's reflection and the mug here, just like the tabletop itself. This gray tabletop is very reflective, just like a mirror. It reflects the objects that are put on it. So there's a single object here, and these three objects are very simple. So I designed this, what I just did was put these three objects here, and I downloaded these from TurboSquid, the horse model as well. They come, when we download a model from TurboSquid, there are certain aspects that we download. So one of them is the geometry of this object. How do we store the geometry of such a mug? Can we have a mathematical formula to do that? Probably no. If you zoom in on this, let me zoom in, you see that the coffee mug is actually not that smooth as we perceive when we perceive it far away. It's actually made up of some small polygons. So usually this is one way to model these complex objects. We use very small polygons and the coordinates, the vertices of these polygons make up a very huge file. For example, let me show you the horse model. This is the horse model, which is a polygonal model. So this, let me zoom in here so that you can see better. So this is a certain three-dimensional object model. So this is what I mean by a virtual object. It's nothing but numbers. So you pay $39 for these numbers. Okay, I mean this horse was free, mug was free. I didn't pay anything for neither of these objects, but certain models are pricey because they have very nice details on them. Their material definition, and apart from the geometry, the only thing we have in this file is the geometry, the color information or different texture if it has different colors in different places. It's not apparent in this format, so in this virtual object. So this is the simplest way to represent a virtual object by just its geometry. Geometry means this. Let's see, what does it mean? It's format. This is the header. So the coordinates are float. It has 11,216 faces. A face is one of these small polygons. So a face may be the most common polygons that people use in generating these virtual objects are triangles and quadrilaterals, which means that it's either a rectangle or a trapezoid. So a polygon with 4 vertices is a quadrilateral, or in short, quad. So if you search for quad mesh, so that's the keyword that you should look for. Quad mesh. So that's what quad meshes are. So here's an example, quad mesh. So this ugly bunny, I think that's one of Pixar's, from one of Pixar's shorts, if I remember correctly, is, okay. So as you can see, it's composed of polygons with 4 vertices. Another thing is triangular mesh. These are the most common ways to represent complex models with small polygons. Look at this bunny. So this bunny is also very famous. So certain objects, virtual objects, are like hello world of this computer graphics scene. One of the most famous objects is the Utah teapot. You may have heard about this. So this is the Utah teapot, and the actual teapot is, I think it's somewhere in a museum in Utah. So it was probably generated by 3D scanning a real model. So that's another thing. Sometimes another way to generate these 3D models is by using 3-dimensional scanners, which is going to go over a real object. You can have a real object like this, and you may have a 3D scanner going around it and identifying the points on the surface, and then you can have a surface mesh by connecting these points into either triangles, again polygons, or quads. Okay, so this is what we mean by virtual objects. So, and there are really nice objects here. Now, if you search for price, there are 162 free coffee mugs. So this is free. You get free cappuccino cup if you want cappuccino, for example, and maybe we are going to replace our mug, which we introduced like 5 years ago to this course, with this cappuccino cup here. So how can you download it? So this is a virtual object. If you download it, it comes with different formats, FBX, OBJ. So it needs you to register an account. So I already have an account here. It's free to register. If you want to play with different models, you need to search again. Coffee mug. So I think I'm logged in this time. All right, where is my free cappuccino mug? I click on free again, and here it is, a free mug for you to download. All right. Oh, these are the other things that I downloaded earlier, I think. So, oh, I have a Formula One racer car, which is also free. Head model. So these are the other. Can I just download one of them? Okay. Yeah, for example, in Blender. So there's a Blender version, there are other versions. So it comes in different formats. It comes with a texture map, but I'm just going to download this OBJ file, which is a common format. So it's here on my desktop. It also comes with a material file. There's a material, there's an OBJ file. This is 448 kilobytes. What I'm going to do is I'm going to open it with, since these are three-dimensional objects, they're not like, you can just, you need a specialized viewer to view them. And one of the specialized viewers I like a lot. If you want to play with these 3D models, I suggest you also install this program, which is called MeshLab, which is very lightweight, and it comes with a lot of tools on it. Okay, it's MeshLab. So let me get this cappuccino cup here. Okay, now if I open import mesh, when I say import mesh on my desktop, it should be able to get this cappuccino cup object. When I say open, there were some materials definitions were not found. A default white material. So since I did not extract the material file, probably there were references to that material file within the OBJ file. So that's why it couldn't find it. But here, just use white material, and here's our cappuccino cup. Look at it. You can interact with it in real time, and it's, I think, a quad mesh. You can see it's composed of these small quadrilaterals. Okay, and it looks really smooth, but the reason that it's smooth is it has many, and the number of quad meshes are more. I mean, you get smaller ones in order to have high detail in those areas. Okay, less detailed areas may have larger quads. But here our virtual model. Okay, so if you put this virtual model is again nothing but a bunch of numbers like these. The coordinates, three-dimensional coordinates of the vertices. So that's another thing we need in order for these virtual objects to come alive. We need a coordinate system. And the most widely used coordinate system that we will also be using in this course is the Cartesian coordinate system, which is basically three axes, major axes, which are x, y, and z. On the slides, you're going to see a z-axis showing in the reverse direction. That reverse direction is sometimes done in the latest stages of the rendering process, but this is the most widely used coordinate system with the acronym right-hand coordinate system. Okay, right-hand coordinate system means that if you have your thumb as your x-axis and your index finger as your y-axis, your middle finger is pointing, it shows you the z-axis, which is pointing towards you. So this is just a convention. Okay, you could have actually, in order to have a valid coordinate system, the only requirement is that you need to have three axes that are orthogonal to each other. They are 90 degrees, because this orthogonality assures that knowing the x-coordinate of some object, you cannot, there's no information about the y-coordinate or the z-coordinate if you just know the x-coordinate. Okay? And so these three information are independent from each other. Sometimes this orthogonality means independence. They are three aspects of some information that we seek. For example, if I have a point here, if I have a coordinate system, by the way, in order to have this coordinate system, I need to also have an origin defined, saying that this is the 0, 0, 0 coordinate here. And another thing is I need to have my units. For example, this point here, can you predict its x coordinate value? No, you need to have the unit vector on the x direction to predict that. For example, if the unit vector, in other words, you need to have that on this x-axis, this is where 1 is, this is where 2 is. Okay, it could have been like this. This is where 1 is. In that case, its coordinate, x coordinate, you can predict it to be 0.9 or something. But if your unit vector is this, in this direction, 1, 0, 0 direction, if this is where that vector ends, then you will predict the x coordinate of this to be like around 2 point something or 3. Okay, so in this coordinate, all these numbers that you see here, they make sense in some coordinate system. So there is obviously there's the shape of this cup will not matter if you change the coordinate system. So there may be the transformation between coordinate systems. So the geometry, for example, if I add, what would happen if you add number 5 to the value of 5 to all the x, y, z coordinates of all these vertices? Would it change the geometry of the cup? No. It will just move the cup 5 units to the right. I mean, in some coordinate system, it will just move it. So certain transformations we are going to see do not change. It really does not matter. These values, they are not really sacred, unchangeable values. The geometry here, they are just given to us in some local coordinate system of the mug. For example, the origin may be the center of the cappuccino mug, a cappuccino cup, or somewhere else. But here, these are the vertices. The vertices are first listed. Let's take a look at the format of this file quickly. But basically, this is not the cappuccino mug. This was the horse model. But if you just save it as you can export mesh. If you export mesh as a standard Stanford polygon file format, cappuccino cup. Let's say save. There are different things that you can do. I can have ASCII. Well, why can't I change ASCII? I cannot. It just have texture coordinate. I don't want this. Vertices. I don't want the normal vectors. Face. I don't need the color value. Wow. This somehow it has to just need to write it binary. I just wanted to show you the numbers for this, but it will look very similar. So if you look at this format, the vertices are listed first, and at some point we need to define the triangles that make up the horse. Where are they? So right here. So these are all the vertices. There are like 5,000, around 5,000 points. If you just visualize those points, you would, in these three dimensions, you would see 5,000 points that are just, it will be just a point cloud that will just resemble a horse. But here are the information that tells you which of these vertices in triplets make up triangles. So this 3 here means that it's a triangular polygon, it's a triangle. We could basically, this polygon model format allows us to have a combined version of triangle and quad mesh. Some of the polygons may be quad, some of them may be triangles. It allows you to do that, this format. And it tells you, for example, vertex number 4, vertex number 2836 and 1406. These 3 vertices are buddies. They make up their triplet, then they make up this triangle. And these are all the triangles. So there are around 10,000. Actually, we knew the number of faces, like, right? 11,000. So this is the number. So if you add up these numbers, you will see all the triangles. So this is just, the geometry is just this. This is our virtual object. And our goal will be to write programs to read these virtual worlds and generate images that look like this. Okay, so this is the output of your first assignment. It will be something like this. Maybe you may change the scene. So how can I say I designed the scene? I didn't model this horse mug. I didn't model horse and mug. I didn't model these. But what I just did was, for example, I transformed them. The horse was, for example, 10 times larger, or maybe I think the mug was 10 times larger than the horse model, because of the fact that each modeler, there's no standard coordinate system for modeling objects. So every time we're modeling these things, there's a local coordinate system. The horse actually was lying on sideways. It wasn't upright like this, so the XYZ coordinates was mixed was different than the mug. Therefore, if you just put these objects together, put them in a single file, polygonal file, what you may end up at the end will be a horse mug inside the coffee mug, lying sideways, 10 times larger. So designing a scene basically means that you have your model, you move it 10 units this way, you scale it down 10 times, you rotate it 90 degrees around the z-axis. So all these three things that I told you, for example, moving the horse 5 units to the left, rotating it 90 degrees around z-axis, scaling it down 10 times. All these things actually are called transformations, geometrical transformations that we will see. We will spend a week or two on these transformations, and we will see that the things that I say verbally will be nothing but multiplying the vertices of each vertex of this horse, those 5,000 vertices. If you multiply each of them with a 4x4 matrix, we'll see why it is 4x4. Multiplying with a single 4x4 matrix will establish all these transformations in one shot. Okay, we will see how we can compose transformations and how we can have those transformations as matrix multiplications. So this is how mathematics will be related to what we will be doing in computer graphics. But as I said, the mathematics is not very complicated. It will not be complicated because it will just be if you know how to multiply your matrices, some certain properties of matrices, you will do fine. Okay, so this is what I mean about I design. I put two large triangles, so this tabletop is nothing but two very large triangles. I did that, and I put these two balls in. Actually, I put these two spheres in these locations. I put this cube by myself, and I placed them on the table in certain positions. It's not very difficult to design such a scene, right? You can also do that in tools like Blender, or you can do it manually after you download these objects. All right, so our goal will be to simulate cameras, to take pictures, to take photos of virtual worlds. And before we go on to a 10-minute break, I just want to show you another thing. Well, the certain properties we have here. Look at this. This is another, oh, not this one, not the wireframe one. This is the input file. I think this one. Yeah, if you look at this, it looks like a similar scene, but the mug this time is sideways. I think it was another figure that I wanted to show. I think it was this one. Yeah, look at this one, a more close-up view. If you zoom in on this, the individual polygons are not visible at the surface. The surface really looks smooth, but the silhouette still seems jagged, like there are some things at the silhouette, but the surface, it seems, you don't see those boundaries of the polygons. So we will apply lots of cheats, tricks to establish that. There are actually the geometry itself is made up of polygons, but we will just fool the vision system of our cameras to treat as if it's a smooth surface. So we will see these algorithmic tricks to be able to generate these. And such smoothness is good on a mug like this, but it also has a bad side effect on this cube, right? I mean, this cube corner, there should be a sharp corner at this edge of the cube, but it also seems like it's smoothed. So maybe in certain objects we shouldn't have this smoothing. By the way, the jaggedness of this is not due to polygons, it is due to the line drawing algorithm, which is doing certain discrete things at every time step. So probably the resolution of this image is not that high. That's why we see these line boundaries as jagged lines like this. But why is this image bad compared to these ray trace one? There are some obvious things here, right? For example, there are no shadows here. Yeah, no reflections, no shadows. So shadows and reflections are two different things. So maybe you didn't notice, maybe the reflections were the first things you notice here, because reflections are really like getting to your eye here. It's everywhere there are reflections, but there are other things that are really subtle. The shadows. Shadows are, we are going to generate shadows a little bit different than the reflections, but all these, for example, generating reflection, generating shadow, we'll do it in code. We'll see a simple algorithm to be able to generate shadows. For example, in OpenGL, by default, there are no shadows. The OpenGL graphics library, there are no shadows by default, so you need to write some additional code to do it manually by yourself. There are no reflections, so these shiny parts on the horse, they are not reflections, okay? They are, I mean, they're not reflections of other objects. These are also called reflections, which are called specular reflections. The light ray is making these spots more shinier, because the way these polygons are oriented, the light rays may come towards our camera stronger. We are going to see such specular reflections. We are going to talk about those. But this is all how light interacts with surfaces of objects, how they reach our eye. This is what the course is about. There's obviously a lot to computer graphics, like it's not always generating these static scenes. How can you generate dynamics here? For example, how can you have your camera have a fly over this scene? How can you have this mug shatter into pieces when it falls onto this table? So all these things, the animation, make the computer graphics a very difficult but also very enjoyable area. In computer games, there is animation all the time, in movies as well. So I think it's now a good time for a 10-minute break. Okay, I will stop recording, but I will keep my WebEx meeting on. I will stop sharing. If you have questions, you may ask in chat box or unmute yourself. But yeah, I will be here during the break, but I will just stop recording this. Let's have a 10-minute break, and we will continue the lecture at 10:45, and I will go over our slides.